In the beginning, before galaxies spun like cosmic whirlpools, before planets found their orbits, before time itself had meaning, there was darkness. A deep, silent nothingness stretching farther than imagination could ever reach. And then, from that darkness, came a spark, small, faint, almost fragile. But that spark ignited something magnificent. It ignited the stars. These glowing giants are more than just distant lights decorating our night sky. They are the engines of the universe, the cosmic factories that create the very elements that make life possible. Every atom in your body, your bones, your blood, your heartbeat, was once forged inside a star. The iron in your blood, the oxygen you breathe, the calcium in your bones, all of it created in the fiery heart of a celestial titan that lived, burned, exploded, and died. But stars don't simply exist. They live. They grow. They transform. They collapse. And they leave behind stories written in light across billions of years. Today, we're going to follow that story from the very beginning to the very end, through clouds of gas so enormous they could swallow our entire solar system, through nuclear furnaces hotter than imagination, through violent deaths that shake the universe, and into the mysterious voids where even light cannot escape. This is not just a journey into astronomy. This is a journey into our own cosmic origins. Because every star begins the same way, as a silent cloud drifting in the dark. And every star ends with a final breath that echoes across light years. But what happens in between is nothing short of a miracle. Some stars grow to become brilliant blue giants that burn with unimaginable power. Others shrink into small, steady embers that glow quietly for trillions of years. Some explode into supernovas brighter than entire galaxies. Others collapse into black holes, cosmic monsters capable of bending space and swallowing everything around them. Every star is a universe of possibilities, a story waiting to be told. And today, you and I are going to tell that story. I'm Sada, and you're watching the FJA universe, where the mysteries of space become a journey you can feel, imagine, and experience. In this video, we'll explore the 5 stages every star goes through, from its birth in massive nebula nurseries all the way to the dramatic moment of its death. You'll see how stars are born, how they burn, how they age, how they transform, and finally, what remains after their final explosion. So sit back, turn up the volume, and get ready to fly millions of light years across space and time. Because the life of a star isn't just science, it's the most beautiful story the universe has ever written. Let's begin. Long before a star is ever born, long before its light cuts through the darkness of space, there exists a kind of cosmic silence, a silence so deep, so ancient, that it feels almost alive. This silence fills the vast regions of space known as molecular clouds. These aren't the thin, empty spaces we imagine when we think of the universe. These are enormous, dense regions filled with gas, dust, hidden shadows, and countless mysteries. They stretch for hundreds of light years, drifting slowly, quietly, like colossal ghosts wandering through the universe. Inside these clouds, nothing seems to move. Nothing seems to grow. It looks like a place forgotten by creation itself. But this stillness is deceptive, because deep inside, the seeds of stars are waiting. Waiting for the moment the universe whispers, begin. A star's life doesn't start with fire. It starts with a collapse. Somewhere inside this giant cloud, something triggers a disturbance. It could be the shockwave of a distant supernova. It could be the slow pull of gravity over millions of years. Or even the collision of 2 massive clouds drifting through the galaxy. Whatever the cause, the moment that disturbance hits, the gas begins to contract. What was once calm becomes restless. What was once still begins to fall inwards. Gravity, the oldest sculptor in the universe, begins its ancient work. Slowly, the cloud fragments into smaller pieces, each one destined to become a star. These fragments grow denser and heavier with every passing moment. Dust grains collide. Gas molecules squeeze together. Temperatures begin to rise. And at the center of each fragment, a faint glow forms. Not a bright light, not yet, but the first sign a star is beginning to take shape. This early form is called a protostar, the baby stage of every star that has ever existed. At this point, the protostar is hidden from the universe, wrapped inside a thick cocoon of dust that absorbs all its light. If you looked at it with human eyes, you wouldn't see anything. But with infrared telescopes, you can see the warm glow of its forming core, a tiny flame waiting to ignite. And inside this growing sphere of gas, something extraordinary begins to happen. Pressure builds. Heat intensifies. The core grows hotter and hotter, millions of degrees hotter. Hydrogen atoms, once floating freely in the cloud, are now being forced so close together that they begin to fuse. And that moment, that single moment when hydrogen atoms merge for the first time, is the moment the star takes its first breath. But this process is anything but peaceful. As the protostar grows, it absorbs material from the disk of gas swirling around it. Streams of matter spiral inward while powerful jets shoot outward from its poles, blasting space with beams of charged particles. It's chaotic, violent, and beautiful. This young star is still finding its balance, still learning how to shine. Around it, the leftover material begins to organize itself. Some forms planets. Some becomes moons. Some remains as dust drifting across the newborn solar system. But at the center of all this activity is the star, still fighting to ignite fully. For millions of years, it struggles between collapse and expansion. Gravity tries to crush it inward. Heat tries to push outward. The star trembles in this cosmic tug-of-war. But eventually, one side wins. With a sudden burst of energy, nuclear fusion stabilizes. The star enters what astronomers call the main sequence, the longest, calmest, and most stable period of a star's life. This is where it shines steadily, produces its light, and begins the real journey of stellar existence. But before that stable future, the star must survive its chaotic childhood. Inside the collapsing cloud, dozens or even hundreds of stars may form together, like siblings born in a cosmic nursery. They influence each other, tug on each other with gravity, sometimes even colliding or stealing material from one another. Massive stars begin forming quickly, burning hotter and brighter. Smaller stars take their time, slowly gathering enough mass to ignite. Some fragments fail to become stars at all. They become brown dwarfs, objects too large to be planets but too small to ignite true fusion. They live forever in the dim twilight between stardom and darkness. But for the fragments that do succeed, something sacred begins, the transformation of gas into fire. And then, finally, the moment arrives. The core temperature reaches around 10 million degrees. Hydrogen nuclei begin to fuse into helium. Light bursts outward. The protostar stabilizes. And the thick cloud around it begins to clear. After millions of years of being hidden, the newborn star finally reveals itself to the universe for the very first time. It is still young. It is still unstable. But it is alive. As the star shines for the first time, the surrounding nebula glows with colors, reds, blues, purples, creating breathtaking cosmic landscapes. These illuminated clouds, like the Orion Nebula or the Eagle Nebula, become some of the most beautiful scenes in the universe. Each glowing pocket of light marks a newly born star. Every star you see, every dot shining in the night sky, once looked exactly like this. Silent, hidden, waiting for the moment gravity would ignite its future. But the journey doesn't stop here. Once stable, the star begins a new chapter of its life, one defined by balance, energy, and time. The star burns through the hydrogen in its core slowly, steadily, like a cosmic heartbeat that continues for billions of years. During this phase, it becomes the shining, stable star we all recognize. The Sun, for example, is currently in this long, peaceful middle age. It has been shining for 4.6 billion years and will continue for billions more. But every star, no matter how small or large, begins exactly where our story began. Inside a cold, quiet cloud drifting through the galaxy. A star's birth is a miracle of physics and creation. A transformation from darkness into light. From dust into brilliance. From silence into a cosmic song that travels across endless space. This is the first step in the incredible journey of a star. And now, as we move forward, you'll see how that young, glowing sphere evolves. How it grows stronger, larger, brighter, and eventually faces a destiny more violent and astonishing than anything we've seen so far. When a fragment of a molecular cloud begins to collapse, it enters one of the most dramatic and least visible phases of a star's life. From the outside, a protostar looks like nothing more than a glowing ember wrapped in a blanket of dust. It is hidden so deeply inside the cloud that even the most powerful telescopes cannot observe it directly in visible light. Everything that happens in this stage happens behind a veil of darkness. But deep inside that dark cocoon, the universe is performing a delicate but violent balancing act. One that decides whether the object will become a shining star, a failed brown dwarf, or something even stranger. The collapse that began in the previous chapter continues here, but it becomes faster, hotter, and more chaotic, and for the first time in its lifetime, the future star begins to generate real heat, not from nuclear reactions, but from the brutal physics of falling inward. As the clump pulls in more material, its rotation increases, just like an ice skater spinning faster when they pull their arms in. This rotation gives rise to a swirling disk of gas and dust around the growing core. If you could zoom in close to one of these young protostars, the sight would be mesmerizing. Streams of matter would be spiraling inward, slamming into the forming star's surface at tremendous speeds, heating it to thousands of degrees. The protostar glows in infrared, giving off warmth even though it has not yet turned on as a star. This glow is what astronomers detect with infrared telescopes like James Webb. It is the faint heartbeat of a star that hasn't yet learned to shine. Gravity compresses the protostar more and more, raising the pressure in its core. With more pressure comes more heat. At first, the temperature is only a few thousand degrees, nowhere near hot enough for nuclear fusion. But the trend is clear. Every hour that passes, every atom that falls inward, every shock wave that rattles through the cloud pushes the protostar toward a critical threshold. Inside the core, hydrogen atoms begin to move faster and faster, colliding more violently. The protostar is like a boiler being heated from the outside. Gravity is the flame, and the supply of fuel is endless as long as the surrounding molecular cloud continues feeding it. But not all protostars will reach the temperatures needed for fusion. Many simply don't accumulate enough mass. If the collapsing clump runs out of material or the surrounding cloud gets dispersed by nearby stars, the growing core may fall short of the 0.08 solar masses needed for hydrogen fusion. In this case, the protostar becomes a brown dwarf, a failed star, glowing faintly with the heat of collapse but never able to ignite true starlight. These worlds are dim, cool, and mysterious. Tens of billions of them may be wandering the Milky Way, invisible to the naked eye, each representing an attempt at stardom that never quite succeeded. For protostars that do achieve enough mass, the collapse continues relentlessly. The disk around the protostar flattens further, and in many cases, clumps within the disk begin to form planets, moons, or even companion stars. This is why binary star systems are far more common than single stars. Like our sun, gravity doesn't tend to make just one object, it tends to make families. Many protostars grow up with siblings orbiting nearby, forming the complex gravitational dances that astronomers observe across the galaxy. As the protostar continues to contract, magnetic fields begin to twist and tighten around it, channeling some of the infalling material into powerful jets that shoot out from the poles. These jets blast through the surrounding cloud, carving tunnels of empty space through the darkness. The sight is spectacular. If human eyes could see it, it would look like a cosmic lighthouse tearing open the shadows. These jets also play a crucial role. They slow down the star's rotation so it doesn't spin itself apart, and they help disperse the remaining gas and dust around the protostar, allowing the young star to eventually emerge into view. Meanwhile, the core continues to heat, and here is where the balance becomes critical. The protostar is wrestling with the laws of physics themselves. Gravity demands collapse, pushing everything inward. But as the temperature rises, the protostar's internal pressure pushes back. These two forces, gravity pulling in, pressure pushing out, engage in a cosmic tug-of-war. For most of the collapse, gravity wins. But the growing heat inside the core strengthens the resistance. When the protostar's core reaches around 10 million degrees Celsius, something extraordinary happens. Hydrogen nuclei begin to fuse into helium. In that moment, a star is born, not slowly, not gradually, but in a sudden ignition of nuclear fire. This ignition is the defining moment of a star's existence. It marks the transition from protostar to main sequence star. When fusion begins, the star stabilizes. The outward pressure created by nuclear reactions balances the inward pull of gravity in perfect equilibrium. This is known as hydrostatic balance, and it is the condition that allows a star to shine steadily for millions or even billions of years. Before fusion, the protostar's life is chaotic and unstable. After fusion, it becomes a beacon of energy and stability, lighting up the cosmic darkness. Once fusion stabilizes the star, the violent jets slow and eventually stop. The surrounding disk thins out, leaving behind planets, asteroids, and other debris. The star sheds the last shreds of its dusty cocoon and emerges as a brilliant, newborn sun. Its light now pushes back against the molecular cloud that once gave it life, creating cavities of glowing gas and sculpting the nebula into complex shapes. The universe is full of these newborn stars, but the process is so slow and so deeply hidden that most people never realize how dramatic it truly is. Every star you see at night, every twinkling point of light, began its journey as an invisible knot of gas buried inside a cold, dark cloud. Every star had to survive collapse, chaos, rotation, magnetic violence, and the crushing weight of gravity just to reach the moment where fusion could ignite. And every star carries the scars of its birth for the rest of its life. The igniting of fusion is not just the birth of a star, it is the beginning of the cosmic engine that powers the universe. Fusion inside stars creates the heavy elements that make planets, oceans, air, and life itself possible. In that sense, the birth of a star is also the first step toward the birth of everything that exists. The atoms in your body, carbon, oxygen, iron, calcium, were forged in the cores of ancient stars that once went through this same violent childhood. You are, in a very literal sense, the product of starlight learning to organize itself into the elements of life. Now that the protostar has ignited and become a main sequence star, the next phase of its life begins, its longest, calmest, and most predictable era. But don't let the word calm fool you. What happens inside a main sequence star is anything but peaceful. It is a ceaseless nuclear inferno, a constant balancing act, and the very mechanism that shapes galaxies and defines the fate of solar systems. In the next chapter, we will follow our newly born star as it enters this long middle chapter of its life, a phase that determines how bright it will shine, how long it will live, and what kind of legacy it will leave behind in the cosmos. The young star, freshly ignited and shining for the first time, has finally entered the longest and most peaceful chapter of its existence. After surviving the violent chaos of its birth, the collapse, the collisions, the jets of expelled material, the desperate struggle between gravity and pressure, it now settles into a delicate but stable balance. This balance is the quiet triumph of a star's early struggles. It is the moment the universe takes a breath and allows the star to simply exist. This period is known as the main sequence, but those words hardly capture the subtle beauty of what this stage truly represents. For a star, this is life itself. Inside its core, hydrogen atoms fuse into helium at a steady, controlled rate. Each fusion reaction releases light and heat that travel outward through layers of plasma, bouncing through the star's inner regions for thousands, even millions of years before breaking free into open space. The star is no longer hidden behind dust or wrapped in the dark cocoon of a collapsing cloud. It shines openly now, proud and steady, releasing the energy that will shape everything around it. The light you see from stars across the night sky comes from this exact phase of their lives, the middle age of stellar existence. In this stage, the star is like a candle that burns without flickering. It may tremble slightly, shift its surface patterns, create sunspots and storms, but its overall brightness remains constant. This stability is what allows planets to form and evolve. It is what allows atmospheres to develop, oceans to exist, and life, under the right conditions, to emerge. For billions of years, the star will maintain this consistent output of energy, a cosmic heartbeat that never misses a rhythm. But not all stars live this peaceful life equally. Size determines destiny. A small star, much smaller than our sun, burns its hydrogen fuel slowly, carefully, almost cautiously. These stars, called red dwarfs, can live for trillions of years, longer than the current age of the universe. They shine faintly, with a calm red glow, but they endure far longer than any other stellar type. Their flickering red light may seem weak next to the brilliant blue giants, yet their lifespan is unmatched. If longevity were the measure of power, red dwarfs would be the rulers of the cosmos. Stars like our Sun take a middle path. Not too slow, not too fast. They burn steadily for roughly 10 billion years, bright enough to warm entire solar systems, but not so intense that they burn themselves out quickly. Our Sun is halfway through this stage, living in its cosmic afternoon. It has enough hydrogen fuel to continue shining for billions more, and because of this stability, Earth has enjoyed a long, warm, and nurturing environment, a rare luxury in an often unforgiving universe. But then there are the massive stars, the giants so large and hot that they seem impossible. These stars may start their lives 10, 20, or even 100 times bigger than our Sun. They blaze with a brilliant blue-white light, hot enough to outshine entire clusters. But this brightness comes at a cost. They burn through their hydrogen fuel with terrifying speed, consuming in a few million years what smaller stars stretch over billions. These giants live fast and die young, their main sequence stage passing like a brief flash of lightning in cosmic time. Yet whether small, medium, or massive, all stars share the same purpose during this phase: the steady fusion of hydrogen into helium. And as long as this process continues, the star remains stable, neither collapsing inward nor expanding uncontrollably. It maintains a perfect equilibrium, gravity pulling in, fusion pushing out. A balance so precise and delicate that even the slightest change in its core temperature could send the entire star into chaos. But for now, the balance holds. The star continues its serene glow. Around the star, planets take shape. Dust grains collide, forming rocks, forming mountains, forming worlds. Some become barren and cold. Some become fiery and volcanic. Some grow thick atmospheres. And maybe, on one of these planets, life begins as single cells, slowly climbing the ladder of complexity over billions of years, all while the star watches silently from above. This is the era when a star becomes a creator. Its light fosters energy. Its warmth maintains stability. Its gravity organizes entire solar systems into elegant patterns of orbits. Without the main sequence, the universe would be dark, chaotic, and lifeless. This stage is the cosmic equilibrium that makes everything else possible. It is the quiet engine driving galaxies forward, one stable star at a time. But even during this peaceful period, changes slowly unfold deep within the star. As hydrogen in the core is consumed, the balance starts to shift. At first, the change is incredibly slow, almost imperceptible. The core accumulates helium, which is heavier and sinks inward, increasing pressure. The star burns hotter to maintain equilibrium. Its outer layers expand slightly. Over millions of years, the star gradually grows brighter. The Sun, for example, was 30% dimmer when Earth first formed. Back then, Earth was colder, yet life still managed to begin. As the Sun brightened, Earth warmed, oceans stabilized, and ecosystems flourished. In massive stars, these internal changes are much more dramatic. Fusion runs faster, temperatures rise more quickly, and the star's brightness can increase significantly over a short time. But even these violent changes are small compared to what awaits in later stages. For now, the star is stable. It shines with purpose, warming worlds, illuminating nebulae, and contributing to the grand glow of its galaxy. If you were standing on a young planet orbiting such a star, you would see a sky filled with star clusters and glowing dust, the remnants of the star's birth cloud still drifting nearby. Over millions of years, these stars slowly separate from their siblings. Gravity pulls them into new orbits around the galaxy. Some drift alone. Others remain in pairs or groups. The universe reshapes itself constantly. As the star travels through the galaxy, it encounters regions of dust, cosmic rays, and magnetic fields. It moves through spiral arms and quiet interstellar deserts. It pulls asteroids, comets, and smaller bodies into orbit. It protects its planets with solar winds. It creates magnetic storms. It ages slowly but steadily, one fusion reaction at a time. Life, if it exists, evolves with its star. Everything depends on the star's stability. A dimming star freezes worlds. A brightening star scorches them. A violent star destroys everything. But during the main sequence, life has its best chance. Millions of species rise and fall, ecosystems flourish, civilizations may arise and disappear, all in the span of a single chapter in the star's long journey. Eventually, the hydrogen in the core becomes scarce. At first, the star compensates by burning hotter. But the balance begins to falter. What was once perfect equilibrium becomes fragile. The star starts to expand. The next chapter in its life begins to awaken, a stage far different from this long era of stability. But for now, during this main sequence life, the star stands as one of the universe's greatest achievements. A stable, glowing engine of creation, light, warmth, and life. When the balance finally breaks, the star's peaceful life will end. And what comes next is far more dramatic than anything before. The stable glow of a main sequence star cannot last forever. Time, relentless and unstoppable, begins to chip away at the delicate balance maintained within the star's core. Hydrogen, the fuel that has sustained it for millions or even billions of years, gradually depletes. As the core loses its supply of this simple element, the equilibrium between gravity pulling inward and pressure pushing outward falters. The star can no longer hold itself steady, and the first signs of transformation appear. For some stars, these changes are subtle, almost unnoticeable. For others, especially the massive ones, they are violent and dramatic, heralding a new, unpredictable chapter in their existence. As the hydrogen fuel in the core diminishes, the star starts fusing hydrogen in a surrounding shell while the helium core continues to contract. This contraction increases the core temperature, which in turn pushes the outer layers outward. The star swells, expanding into what astronomers call a red giant. Its surface cools slightly, giving it a reddish hue, while the core grows hotter and denser. This expansion is not gentle. It is a slow, powerful inflation that can increase the star's radius hundreds of times larger than its original size. If a star like the Sun were to become a red giant, it would swallow the inner planets, including Mercury, Venus, and possibly Earth, enveloping them in its fiery embrace. Inside the expanding star, fusion continues in complex layers. Hydrogen burns in a shell surrounding the helium core, while helium itself awaits temperatures high enough to fuse into heavier elements. The star becomes a layered furnace, with each layer representing a different stage of nuclear burning. In these layers, heavier elements like carbon and oxygen begin to form, setting the stage for the star's next transformation. The energy produced in these reactions pushes against gravity, temporarily stabilizing the star even as it grows in size and complexity. Red giants are among the most visually striking stars in the universe. From a distance, they appear luminous and enormous, their warm glow dominating the night sky. Their brightness increases dramatically, outshining their previous main sequence luminosity many times over. Yet, despite this outward grandeur, the internal structure is fragile. The core continues to contract, and each new layer of fusion brings the star closer to instability. For massive stars, the process accelerates. Their cores heat to hundreds of millions of degrees, fusing heavier and heavier elements in a rapid, successive sequence. For stars larger than 8 times the mass of the Sun, this progression is a countdown to something catastrophic, a supernova. As the red giant phase progresses, the outer layers of the star become increasingly unstable. Pulsations, violent ejections of gas, and the shedding of material into surrounding space are common. These stellar winds can carry away significant portions of the star's mass, enriching the interstellar medium with carbon, oxygen, nitrogen, and other elements crucial for the formation of future stars and planets. In this way, even in its later stages, a star contributes to the ongoing cycle of cosmic creation. The material expelled by these giants becomes the raw ingredients for new stars, planets, and eventually, life itself. For stars similar in size to our Sun, the red giant phase eventually leads to the formation of a planetary nebula. The outer layers drift away gently, glowing as they are ionized by the remaining hot core, which shrinks into a white dwarf. This remnant, no longer capable of fusion, slowly cools over billions of years, fading into darkness. It is a quiet, dignified end, a final testament to a star's life and the enrichment it provided to the cosmos. Massive stars, however, follow a far more violent path. Once the core accumulates enough iron, fusion can no longer produce energy, and gravity takes over completely. The core collapses in a fraction of a second, triggering a supernova explosion, a cataclysm so powerful it can outshine entire galaxies for weeks. The shockwaves from such an event scatter the star's outer layers across interstellar space, seeding it with heavy elements that will one day form new stars, planets, and possibly even life. The remnants of this explosion, neutron stars or black holes, serve as cosmic monuments to the star's existence, bending space and time and affecting everything around them. The red giant phase and its aftermath are not merely the end of a star. They are a transformation that links one generation of stars to the next. The elements forged during a star's life are released into the universe, becoming the building blocks of future stars, planets, and the complex chemistry necessary for life. Every atom of carbon in our bodies, every oxygen molecule we breathe, every trace of nitrogen in the soil, each originated in a star that went through this stage millions or billions of years ago. In this sense, the death of a star is not an ending but a continuation, a necessary act in the eternal cycle of cosmic evolution. For humanity, observing red giants and their remnants provides not only a glimpse into the fate of our own sun but also a window into the processes that shaped our galaxy. Through advanced telescopes, we can see stars in various stages of expansion, nebulae glowing in vivid colors, and remnants of supernovae stretching across light-years of space. These observations remind us that the universe is dynamic, ever-changing, and that every star, no matter how brief or long its life, plays a critical role in the cosmic story. As the star's outer layers drift away and the core contracts, the surrounding space is transformed. New clouds of gas and dust form, ready to collapse into the next generation of stars. The cycle continues, a never-ending rhythm of birth, life, death, and rebirth. It is a cycle that has persisted for billions of years, shaping galaxies, creating planets, and setting the stage for life itself. The star, once a tiny fragment in a dark cloud, has now fulfilled its purpose. It has lived, it has shone, and it has enriched the universe in ways that will resonate for eons. And yet, even as we witness the dramatic transformations of red giants and massive stars, the story of the cosmos is far from over. The remnants left behind, white dwarfs, neutron stars, and black holes, continue to influence the universe around them. Gravity, radiation, and magnetic fields shape the formation of new stars and galaxies, ensuring that the cycle of creation and destruction goes on indefinitely. The life of one star becomes the foundation for countless others, a continuous chain linking past, present, and future in the vast tapestry of the cosmos. After the tumultuous life of a red giant, the fate of a star diverges depending on its mass. Smaller stars, like our Sun, follow a quieter, slower path, gradually shedding their outer layers and leaving behind a dense, compact core, a white dwarf. This remnant, no longer capable of fusion, is intensely hot at first, radiating energy accumulated over billions of years, but it slowly cools over time, fading into darkness. It is a peaceful, dignified end to a long life, a lingering whisper of the star's former brilliance. Yet, even in death, it has left an indelible mark on the cosmos, enriching the interstellar medium with carbon, oxygen, and other elements essential for the formation of planets and life. White dwarfs, although small, roughly the size of Earth, contain a mass comparable to the Sun, making them incredibly dense. A teaspoon of this material on Earth would weigh tons. They are stellar relics, silent witnesses to the past, slowly cooling over billions of years. Their faint glow may eventually vanish entirely, leaving behind a black dwarf, a theoretical object, cold and dark, drifting through space like a forgotten memory of light. In this way, even stars like our Sun, which seem modest compared to cosmic giants, leave behind echoes that continue to influence the universe long after their visible life ends. For massive stars, However, the final chapters are far more violent and awe-inspiring. As the core of a massive star fuses heavier and heavier elements, carbon, neon, oxygen, silicon, the clock runs out. Fusion can only produce energy up to iron, which cannot generate outward pressure when fused. Gravity takes over, collapsing the core in a matter of seconds. The sudden implosion triggers a supernova, a catastrophic explosion so powerful that it can briefly outshine an entire galaxy. The outer layers are violently ejected into space, scattering heavy elements across vast distances. These supernova remnants seed future generations of stars, planets, and even life, continuing the cosmic cycle. The shockwaves from supernovae have the power to trigger star formation in nearby molecular clouds. In a profound twist of fate, the death of one star can ignite the birth of countless others, a literal recycling of stellar material on a galactic scale. The universe is interconnected in ways that are both beautiful and terrifying, a web of creation and destruction that has been woven for billions of years. Stars are not isolated. They are part of a grand cosmic ecosystem, each life affecting countless others in subtle and dramatic ways. Some massive stars leave behind neutron stars, objects so dense that a single teaspoon of their material would weigh billions of tons on Earth. These stars are exotic remnants, composed almost entirely of neutrons, spinning at incredible speeds, and sometimes emitting beams of radiation as pulsars. Other massive stars collapse further, forming black holes, regions of space where gravity is so intense that not even light can escape. Black holes are the ultimate testament to the power of stellar evolution, invisible yet exerting influence over their surroundings, warping spacetime and affecting the motion of nearby stars and gas. The death of a star, whether gentle or violent, is not an end. It is a transformation, a continuation of the cosmic story. Elements forged in the hearts of stars become the building blocks of planets, moons, and life itself. Carbon in our bodies, oxygen in the air, iron in the blood, all were created in ancient stars that lived and died billions of years ago. We are, in essence, made of stardust, a direct product of the life cycles of stars across the universe. Understanding these processes connects us not only to the cosmos but to our own origins, revealing the intimate relationship between humanity and the stars. Throughout this journey, stars teach us about balance, patience, and transformation. They live, they struggle, they shine, and they die, each phase an essential part of a larger cycle. From the molecular clouds where they are born to the dramatic supernovae or quiet fade of white dwarfs, stars are the universe's most magnificent storytellers. They narrate the history of galaxies, the creation of planets, and the emergence of life itself. Observing stars, we witness not only light but the profound processes that sustain the cosmos, a reminder of the intricate and interconnected nature of existence. Even as stars die, their influence spreads across the galaxy. Supernovae enrich the interstellar medium, molecular clouds collapse to form new stars, and remnants like white dwarfs, neutron stars, and black holes continue to shape the motion of matter and energy. The universe is in constant motion, a vast, eternal cycle of creation, transformation, and renewal. Stars are both actors and witnesses in this cosmic drama, their lives short in comparison to the age of the universe but crucial in their impact. In the end, whether a star meets a quiet death as a white dwarf or a cataclysmic explosion as a supernova, its story is inseparable from the story of the cosmos. Stars are not solitary. They are the lifeblood of galaxies, the creators of worlds, the crucibles of elements, and the silent architects of life. Their births, lives, and deaths are the chapters of a universal narrative that stretches across space and time, connecting every corner of the universe in an intricate tapestry of light and matter. By studying stars, we study the universe itself, and in turn, we discover our own place within it. As stars age and move toward the final stages of their existence, the universe begins to show the consequences of their lifetimes. Even during their stable periods, stars influence the space around them in subtle yet profound ways, from radiation and solar winds to gravitational forces. But as they approach the end of their life cycles, these effects become magnified, dramatic, and often spectacular. For massive stars, the universe holds a climax of unimaginable violence. For smaller stars, a quieter, equally significant transformation unfolds. The processes that take place in these late stages define not only the fate of the star itself but also the future of countless other celestial bodies. For stars like the Sun, the red giant phase eventually leads to the shedding of outer layers, creating a planetary nebula. This phase is both a farewell and a gift. The glowing shell of gas expands outward, illuminated by the remnant core at the center. The colors of these nebulae, vivid blues, reds, and greens, are not just beautiful. They are chemical signatures, the fingerprints of elements forged deep within the star over billions of years. Hydrogen, helium, carbon, oxygen, nitrogen, and traces of other heavier elements escape into the surrounding space, seeding future generations of stars and planets. The process is gentle yet profound. The star dies, but the universe gains immeasurably. The remnant at the center of the nebula becomes a white dwarf, a dense, slowly cooling ember of what was once a star. White dwarfs are incredibly dense, containing nearly the mass of the Sun in a volume similar to Earth. Their gravity is intense, their heat enormous initially, and their light can illuminate their surroundings for billions of years. Over time, they cool and fade, eventually becoming black dwarfs, objects that exist only as remnants of a star's former life. Even in silence and darkness, their legacy persists, for the elements they dispersed will give rise to new stars, planets, and perhaps life itself. For massive stars, the story is far more violent. The final stages of these stars are rapid, chaotic, and destructive. As they exhaust their fuel, their cores become dominated by iron, which cannot produce energy through fusion. Gravity overwhelms the star in an instant, collapsing the core in a catastrophic implosion. The outer layers rebound in a supernova explosion, releasing energy equivalent to billions of suns for a brief moment. The shockwaves from these explosions rip through nearby space, triggering star formation in other molecular clouds, compressing dust and gas, and distributing elements forged in the star's core across vast distances. The supernova is both an ending and a beginning, a violent act of creation and destruction intertwined. The remnants left behind by supernovae are some of the most exotic objects in the universe. Neutron stars, composed almost entirely of neutrons, are dense beyond comprehension. A single teaspoon of neutron star material would weigh billions of tons. These objects often spin at incredible speeds, emitting beams of electromagnetic radiation as pulsars. Black holes, formed from the collapse of the most massive stars, warp spacetime itself, bending light and affecting the motion of nearby stars and gas. Even after a star has ceased to shine in visible light, its influence continues, shaping galaxies, star clusters, and the very fabric of the cosmos. The death of a star is not just an isolated event. It is part of a grand cosmic cycle. Elements formed in stars, carbon, oxygen, iron, and many others, are scattered throughout galaxies, becoming the building blocks for new stars, planets, and life. Every atom of matter in our bodies, every drop of water we drink, every molecule of air we breathe has, at some point, passed through the interior of a star. Stars are the universe's great alchemists, transforming simple hydrogen and helium into the diverse elements that make up everything we see. The end of a star is thus not a termination but a transformation, a continuation of cosmic creation. Even the seemingly small and insignificant stars play a role in this ongoing cycle. Red dwarfs, the most common type of star in the universe, burn slowly and steadily, often for trillions of years. Their long, stable lifespans allow planetary systems to exist in relative calm for eons, giving life the chance to develop on orbiting worlds. These stars, though faint and unassuming, contribute to the cosmic balance, providing stability and light in regions of space far from the dazzling brilliance of massive stars. As stars die and new ones are born, the universe evolves. Galaxies rotate, nebulae expand, star clusters drift apart, and cosmic structures shift over millions and billions of years. The life cycles of stars, from birth to death, shape these processes. Each supernova enriches its galaxy, each white dwarf radiates its final energy, each black hole warps its neighborhood. The interplay between creation and destruction, stability and chaos, defines the universe we observe today. Stars are the heartbeat of the cosmos, setting the rhythm of time and space. For us observing from a small planet orbiting an ordinary star, these processes might seem distant or abstract, but their effects are immediate and profound. Our very existence depends on the life cycles of stars. Without the elements they create, there would be no planets, no water, no atmosphere, and no life. Without the stability of main sequence stars, life would have no chance to develop or persist. Every star, no matter its size, is a thread in the intricate tapestry of existence, linking the past, present, and future in a continuous chain of creation and transformation. Even as we study stars in their final stages, from dying red giants to the remnants of supernovae, we witness the enduring power of the cosmos. These distant objects, millions or billions of light-years away, teach us about balance, resilience, and transformation. They remind us that life, growth, and death are not only natural but essential, part of an endless cycle that connects all matter, all energy, and all life. Stars are not merely points of light in the night sky. They are the storytellers of the universe, narrating tales of creation, destruction, and renewal across unimaginable spans of time and space. And as the last gas drifts from a dying star, the core cools into a white dwarf, a neutron star, or collapses into a black hole, the universe prepares for the next chapter. New molecular clouds gather, collapse, and ignite into fresh stars, continuing the eternal dance. The legacy of one star becomes the foundation for the next. In this way, the cosmos is both infinite and cyclical, a vast theater where every star, every planet, and every particle participates in the ongoing drama of existence. The story of a star, from birth to death, is a story of the universe itself, a story of light, matter, and the endless cycles that make creation possible. From their humble beginnings in cold, dark clouds of gas and dust to their brilliant emergence as blazing lights in the galaxy, stars have captivated the imagination of humans for millennia. They are more than distant points of light in the night sky. They are the architects of the universe, the engines of creation, and the crucibles in which the elements of life itself are forged. Every stage of a star's life, from formation to main sequence, to the dramatic transformations of red giants, supernovae, and stellar remnants, tells a story of balance, energy, and transformation on a scale that is almost incomprehensible. Stars teach us that life, even on a cosmic scale, is about cycles. They are born from clouds of gas, stabilized through fusion, and eventually die, leaving behind remnants that will seed the next generation of stars. In this cycle, nothing is wasted. Every atom of carbon, oxygen, iron, and nitrogen, every speck of dust scattered across the galaxy, every particle that forms new stars and planets, everything originates in the hearts of stars. In a very real sense, we are all made of stardust, intimately connected to the cosmos in ways that are both poetic and scientifically profound. For smaller stars, their long, steady lives provide stability, nurturing planets that may someday harbor life. For massive stars, their spectacular deaths reshape entire regions of space, scattering elements and triggering the birth of countless new stars. White dwarfs, neutron stars, and black holes stand as monuments to the power and diversity of stellar evolution, each unique, each vital in its own way. The universe thrives on this cycle of creation and destruction, a rhythm that has persisted for billions of years and will continue for billions more. Observing stars is like reading the history of the universe itself. In their light, we see the past. In their evolution, we glimpse the future. Their stories remind us that even in the vast emptiness of space, there is order, purpose, and beauty. The death of one star becomes the beginning of another, a reminder that endings are never final but part of an ongoing, magnificent cycle of cosmic rebirth. As we gaze at the night sky, every shining star is a storyteller, a witness to the grand tapestry of existence. They illuminate our place in the cosmos, remind us of our origins, and inspire us to explore the vast, uncharted universe. From birth to death, stars are the eternal narrators of the universe, their light carrying the memory of creation across space and time. In understanding them, we understand not just the cosmos, but our own connection to it, and the timeless dance of matter, energy, and life that has shaped everything we know. The story of a star is the story of the universe itself, a luminous, ongoing testament to creation, transformation, and the endless cycle of life that stretches across billions of years and countless galaxies.